So today we're going to work out some issues with regards to the speed of sound and also beginning to start thinking about how temperature might actually play a role. So I'm just going to sort of hand you a formula right now which says, okay, that the speed of sound, that's v sub s, that remember that the v is for velocity, that the speed of sound is equal to 344 meters per second if it's at 20 degrees Celsius. So the way to read this kind of equation, and by the way, this is the same as equation that's kind of on page 10 of your text. You'll see it written out. This would definitely be one to include. You're going to be able to have a crib sheet that you can bring with you for exams, and this would be one of those equations that you want to have written down and master how to calculate the speed of sound given the temperature. One of the things that we can see here is that if the temperature, let's say T, is 20 degrees, then you do 20 minus 20, and so this whole term right here would not actually matter. And you just have 344 meters per second. So in other words, 20 degrees, you might not know it immediately. What does it mean 20 degrees? Is that cold? Is that hot? Well, in Celsius, I would say that's probably a pretty normal temperature. It's going to feel comfortable. Maybe even t-shirt weather, depends. Maybe this is what we call as room temperature. So let's take a look at that, and we'll come back to this equation. So here's the temperature scales here. You can see here on the bottom we have the temperature in Celsius, and above we have the temperature in degrees Fahrenheit. So let's look at a couple things that are pretty familiar here. So, well, where does water freeze? Well, in Fahrenheit we would say it's 32 Fahrenheit, but you see 32 is here, so here's 20, here's 30, and here's 40, so it's right over here is 32. And if you go down, you can see that it's corresponding to 0 degrees Celsius on the Celsius scale. And water boils. I didn't get all the way up here, but you can see that if we were to continue following this thing up here, water would boil at 212 if you went off to the right here, Fahrenheit. And if you followed that down, you can see it's at 100 Celsius. So clearly, once again, the SI units seem superior because water boils at 100 and freezes at 0. It's a lot easier to remember than the number 212 and 32. But in any case, that's something we have to reckon with, and we have to be able to convert back and forth between the two. So I put a couple formulas here. If you had the temperature in Fahrenheit, you can subtract 32 from it, multiply by 5/9, and you will have the temperature in Celsius. If you are given the temperature in Celsius, you can do the opposite. You can actually, this one equation is enough. We could resolve this equation for T sub f by, say, dividing by 5/9, adding 32 to both sides, and we would solve for temperature in Fahrenheit. And I encourage you to do that just to make sure that that's making sense to you. Temperature in Fahrenheit then can be given by just taking that temperature in Celsius, multiply by 9/5, add 32. So for example, if the temperature in Celsius was 0 Celsius, multiply by 9/5, 0 times 9/5 is 0, add 32. That's exactly what this says here. That 0 Celsius is the same thing as 32 Fahrenheit. So hopefully this is helping you to figure out how to convert things. Here's an example down here. If you want to convert, say, 20 degrees Celsius, multiply by 9/5, add 32. If you do this out on a calculator, in fact, why don't I just pull up a calculator here? Got my little, by the way, something that I like to use, but there's of course many options, is I use something called Speed Crunch. Oops, and funny enough, I didn't actually install it on the computer, so I can basically do 20 times 9 divided by 5, and then adding 32, and I get 68. So you can use a built-in calculator to Google. That also works. So that's how we convert back and forth between those two. So by that logic, you can see that 68 Fahrenheit, okay, it seems like pretty reasonable temperature out. It's comfortable. That's 20 degrees Celsius. So we kind of think if there's ever a problem given to you where you're not given the temperature, you can imagine that it's probably at this so-called room temperature, because that's a pretty normal temperature. And the other thing that I want to draw out here is that you see our formula. It basically says that for every degree that you go, let's say you go to 21 degrees, right? Then 21 minus 20 would be 1. For every degree Celsius that you go above room temperature, you pick up an extra speed of 0.6 meters per second. I'm going to do a little like mini review here about this whole units business. Do you remember we were talking about meters per second and trying to think of that in terms of miles per hour? So let's actually figure out, well, what is that 344 meters per second in miles per hour? That's kind of like a nice question to ask, because I mean, we want to make these things meaningful to us. So what we can do here is say, okay, well, I have 344 meters per second, and what I want ultimately is miles per hour. That's really what I want. So I have to figure out how many meters there are in a mile. So one thing that I can do is, remember that we found out before that 5 kilometers is the same thing as 3.1 miles. I know that because I like running, so that's good enough for now. I can say, okay, well, if this is true, then I can say that 3.1 miles divided by 5,000 meters is equal to 1. This is the old multiply by 1 trick. So I'm going to take this fraction here. Notice how I was careful to put the meters on the bottom, because when I multiply this here, we got 3.1 miles divided by 5,000 meters, because 5 kilometers means 5,000 meters. This is going to cancel out the meters, and I'll have 3.1 times this. But now I still have seconds. I need to turn that into hours. Well, I got to think about how many seconds there are in an hour. So this is a good thinking exercise. Can you pause this video and think about and actually calculate how many seconds there are in 1 hour? Go ahead. Okay, we're back. So how did you calculate the number of seconds in an hour? You might have thought, well, you know, I know that there's 60 seconds in a minute, and I know there's 60 minutes in an hour. So it looks like you can multiply 60 times 60 and you get 360 seconds in an hour. Done out more detailed here, you could say that there's 60 seconds per minute, and there's 60 minutes in an hour, and the minutes look like they cancel out, and I'm left with 3,600 seconds in 1 hour. So in 1 hour. So in other words, you could say that this is the same thing as saying that 3,600 seconds equals to 1 hour, or you can say that 3,600 seconds divided by 1 hour is equal to 1. So again, we can go back over here and I can say, oh, looks like I can just multiply that fraction. If the seconds was on the bottom instead, I would just flip this over and then multiply. But here we've got it. Here's 3,600 seconds in 1 hour. The seconds here, my seconds, it's going to cancel out with this seconds. And now I've got just a chain of numbers here. 344 times 3.1 times 3,600. And it looks like the units that are left here are miles and then 1 over hour. So miles per hour. Now the only thing that's left here is that, well, we have to calculate this. So I'm going to go ahead and do that here. It looks like I have 344 times 3.1 times 3,600. And it looks like, ooh, I got some crazy number. I just wonder if I did it correctly. I think so. What is going on here? Oh yeah, okay. No, I missed something. You see? Okay. Let me go back to the camera here. I missed that I divided by 5,000. So this times this divided by that. Good. So let's divide by 5,000, and those are all of our numbers. This is going to be 768 or so miles per hour. And notice that the kind of level of precision that we're going for here is I'm just trying to get an idea. This is going to be divided by 5,000. Good. So the thing I want to sort of drive home here is that the summary of this is that 344 meters per second is pretty much the same thing. I could write almost equal to, but this is close enough to being equal to 768 miles per hour. This is the speed of sound. So you might have also heard of something called Mach 1 before. Mach 1 means the speed of sound. If you did Mach 2, it means 2 times the speed of sound. We'll perhaps talk a little bit later about something called a sonic boom, when an airplane or jet goes faster than the speed of sound. And so it's creating sound, but it's also traveling faster than that. So But anyway, one thing that I want you to notice here is that if you took this number, let's say it's 350, if you basically multiply it by 2, you get the same number in miles per hour, basically, okay? That's just kind of like a nice way to kind of remember it. So, for example, how fast do you walk? Well, I don't know, maybe if you're a slow walker, maybe you do 1 meters per second. Well, how many miles per hour can you walk? Well, 1 meters per second looks like it's approximately 2 miles per hour, mph. So that's kind of a nice way to sort of at least take these units of meters and seconds that maybe you're not as familiar with. I'm thinking of it more in terms of miles per hour. We could also do the same exercise with turning it into kilometers per hour, which would be taking this number and kind of putting it in about by a factor of half or so. About a factor of 2. So in other words, if I did 2 miles per hour, that'd be like saying I could do about 3.5 kilometers per hour. So anyway, so I just want to try to continue to promote that you try to make all these things physically meaningful, so that if you get a number, you can at least say, oh yeah, I kind of know what that feels like. Very good. So so let's see here. I'm going to probably go to our first question here. Yeah, I can see that this will be an issue for some of the later slides. I'll have to go into presentation mode so that you can have a moment to think about what the answer is before the answer is shown, but here I think it's okay. Let's review for a moment. Please try this question. Pause your computer now and see if you can figure out how to express this number. This is a particular vibration that repeats itself in a time interval that's 0.0001 seconds. The vibration has a very, very high pitch, which we'll get to later. It seems like it's oscillating a lot in 1 second. Express this number using scientific notation. Go ahead and pause and come back when you think you've got it. Okay, we're back. So, how do we approach this kind of problem? Well, I'm going to look at that number, 0.0001. Okay, good. And I'm going to get a sheet of paper here. And that number, 0.0001, if I noticed if I had a decimal over here, I might have to move it over 1, 2, 3, 4 just to get it to be over there. So that means that's like taking the number 1 and multiplying by 10 to the minus 4. Let's see if that gets me there. So here's my 1 and times 10 to the minus 4. 1, 2, 3, 4. Correct. That looks like it's the right answer. So 1 times 10 to the minus 4 are also 1e minus 4. All those are equivalent representations of this. And let's take a look and see if we're correct here. So with that in mind, it looks like D might be correct. Let's see if there's any other possible answers that might be correct. Well, this one looks like it might have potential, except that I know that multiplying by 10 is actually going to make this e minus 3 into an e minus 2. So A actually is the same thing as 1e minus 2. Okay, so that's actually not correct. If we were to do, for example, 0.1 e minus 3, that would work. Or if we did 10 e minus 5, that would work. But here it looks like the answer should be D. Okay, so if you got that, give yourself a little congratulations. It seems like you're maybe coming along nicely on being able to handle scientific notation. This is an important part of the class, and it's worth your attention. Make sure that you get this figured out early. As a reminder, there's both a math review and a scientific units review that is available on Blackboard. All right. So here's kind of a funny question for you. When I speak, do the air molecules move directly from my mouth to your ear at this speed of 344 meters per second, or like 770 miles per hour? Is that true? Like, if you shout, is there actually molecules that are coming out of your lungs over to the other person and then like striking them? What do you think? If you're watching this video with somebody right now, pause to see what you both think. Talk it over. All right. So we're back. The answer is no. There are not air molecules moving from my mouth to your ear. If it was the case, then this would be a big problem. I think for a moment in the medical field that people will wear a mask, right, to keep molecules, for example, some water vapor that's in your lungs, from reaching the patient to keep the spread of communicable diseases, right? So occasionally you may see myself or another student wearing a mask in class. Just means that maybe we're feeling a little bit under the weather and we don't want to spread the cold or the flu or so. Also, I might do it as a precaution if I notice that a lot of people are sick, right? So, okay, if you have the if you don't have these air molecules moving directly, well then what is happening exactly? And so you've now had an experience in one of our activities of kind of seeing some visualizations of, well, how is sound really propagating? And you have now this concept that it's actually air molecules that are bumping into each other. So think of it as like a big traffic jam of bumper cars. And one bumper car bumps into the next, which bumps into the next, which bumps into the next. And so not one bumper car actually, say, went anywhere really, it just moved a couple of feet or so, but there's still some motion that happens on the other side. And you can kind of keep that analogy in mind of bumper cars. You're getting a lot closer to what's really happening when sound is propagating. Okay. So then kind of begs the next question is, well, how fast does the air actually flow out of your mouth as you sing or as you speak? You might think, well, I mean, if you blow a candle, you might notice that you kind of blow and there's a little delay. That might be some indication to you that maybe it's slower. So it's actually that it's this vibration that we're creating, that the wave of sound that is actually moving at what's called the speed of sound, whereas the actual airflow out of your mouth is actually much lower than that. And so you can perhaps test this out by holding your hand out in front of you and going, and you might notice that there's a little bit of a delay. And it's like, let's say, half a second delay. So even if I just were to kind of make a guess here, if I pulled out my hand 1 meter in front of me, and it took half of a second, right? Then that's about, oops, I said 1/2 of a second. Then that's about 2 meters per second is the speed of the air coming out of my mouth. Well, it's not very fast. Okay, maybe I was wrong by a factor of 2 or 3 or maybe even 10, but still, this is nowhere close to 344 meters per second. So that's kind of a good way for you to confirm to yourself that the air flowing out of your mouth is in fact much slower than 344 meters per second. It's the speed of the wave, the sound wave. That's the important part. Alright? So, here's another kind of funny question for you. Sunny day. When is the speed of sound faster? Is it in the early morning, midday? Is it around midnight? Or does speed not depend on what time of day it is? So I'm going to give you a moment, pause here, and don't just come up with an answer, but come up with a reason. So if you're writing these things in your notebook, you might say, write in your notebook along. And by the way, these questions need renumbering, but you can just use this as a way to sort of earmark to yourself which question you're talking about. Okay? I'll pause here. Okay, we're back. So on a sunny day, well, I know that if it is a sunny day, I know that the temperature that I'm experiencing. Okay, and let's do something like this. This is the time of day. This is going to be like something like 6 a.m. This will be noon. This will be, I don't know, 6 p.m. something like that. Maybe here's midnight. And you can notice that maybe the temperature, let's do it in degrees Celsius, is probably going to be, let's say here's 20 degrees Celsius, that's our room temperature. Maybe it's a little cold in the morning, right? And then after the sun rises, it kind of goes up, and then maybe it peaks around noon or so, maybe it goes a little bit later, and then it kind of, eventually the sun sets, and it starts to go down again, and then it goes back down to this kind of thing here. So that's kind of what we would expect of the temperature. That sometime around noon, the temperature is the highest, and sometime either around midnight or in the early hours of the morning it would be the lowest temperature. So again, let's remember our formula here that the speed of sound is 344 plus 0.6 times T minus 20, and this is going to be in degrees Celsius. Okay, so I'll just remind you here, this is going to be in degrees Celsius. I'll just end up dropping that eventually. And that this overall number here is going to be in meters per second. So what's interesting about this formula is that you put in something in degrees Celsius, and then this number has some units, like for example meters per second per Celsius or so, such that it converts it automatically. So it's a formula that you can kind of put in one number into your sort of machine. This is kind of the way I think about functions sometimes. And then out comes another thing. So you put in a temperature, and it spits you out a speed of sound. Okay, so that's kind of how this little machine works. Is some stuff happens inside of the machine, and then it spits something out. Okay, so that's going to be a way to think about a function. So, in other words, it looks to me like if I were to plot this function here, it's 344. So here's maybe my speed of sound, and here's my temperature. It looks like there's going to be an overall shifting up because of this 344. And then it looks like there's going to be a line that's proportional to t, and then there's an overall minus something. So it should look something like this, I guess. Right? This is kind of the general shape of this this thing. And of course, this may break down at some very, very low temperature, right? So okay, maybe this formula is like only valid for normal human temperatures, such as like I don't know, maybe when the temperature is like between here and here or something like this. Maybe this is just an incomplete formula that only works in sort of a limited range, but this will be the limited range that will be appropriate for the kinds of things that we're doing in this class. So in any case, the higher the temperature, then the higher the speed. The lower the temperature, the lower the speed. So perhaps you can make some ideas about what's going on here. Is that if you have a very sunny day, then around midday we'll actually expect that the temperature is the highest, and therefore the speed will also be the highest. Good. So if you're getting that, we're feeling good about what's going on, then that's great. If you're not, then please refer to your textbook for a little bit extra supplementary. And also, I'm going to be making some other online resources available as well to try and help. So, all right, let's try another problem. So this is the way that we get better at these problems, is by practicing. And so here it is a cold night. The temperature is 0 Celsius. If you see a flash of light in the distance, and then you hear a boom a second later, how far away did this boom occur? Okay, good. So this is really reminiscent of one of the problems that we did before with the lightning. Remember the lightning and then the thunder? So again, why is it that we have this delay? Well, the delay is because the light and the sound do not travel at the same speed. In fact, the light is traveling very, 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 very fast. Let me give you a moment to try and solve this problem. At least come up with a strategy if you can't figure out how to solve it. And then we'll have a discussion in just a moment. I'm going to go ahead and pause here. Okay, we're back. So here we have the temperature is 0 Celsius. And we see there's a delay between the flash of light and the boom, that boom that we hear, of 1 second. So let's write down some things that we know, and then we'll try and figure out this problem. So okay, so maybe I'll start by drawing a little picture. So perhaps we'll look at it like this. I'm standing over here, and pretty happy looking at these some boom, and then the light gets to me, let's say almost instantaneously, and then the sound gets to me later. Okay, and so we want to figure out, well, what is this distance here to the boom? Maybe it's something for safety that we wanted to figure out. Am I in danger right now? And so this is a good way to estimate. We're also given that the time, I'll write it as t, is 1 second. We weren't really exactly given the speed, but if you remember, we've got a formula for speed. We have 344 plus 0.6 times t minus 20. I'm already going to fill in t as 0, so 0 minus 20, and this will be in meters per second. So this is our formula here, and I've just plugged in for 0 degrees Celsius here. Okay, that's why I put a 0 in there. And you notice that putting in a 0 doesn't make this whole term 0 because it's a minus 20 times 0.6. So what's 2 times 6? Well, that's 12, right? So if we did 20 times 0.6, well, that's like 2 times 10, and then 6 times divided by 10. So actually, that's just 12. So it's minus 12. So if you can't do that in your head, I want you to practice that and try to get a little bit better at doing some of these things. And you're going to see some themes as we go. You'll see it happen again and again. We'll see situations like this, and you might think, oh, I got to get a calculator for that. But then you might actually find that, like, oh, wait a second, 20 times 0.6 is the same thing as 20 times 10 times 6 divided by 10. And then you'd say, oh, well, that's just, I'm sorry, 2 times 10. So 2 times 6 then is just simply 12, right? So you can kind of quickly do those sorts of things in your head. Anyway, if you do need a calculator, it's okay. You will be allowed to use a calculator on exams. I will be providing you with a calculator, and you'll get a chance to practice with those before the exam as well. So, all right, so 344 minus 12. Here's a little chance for me to see if I can do things correctly in my head. Looks like it's 332 meters per second. So even though we weren't given the speed of sound explicitly, it does look like I'm able to figure out what this speed is here, just based on the temperature alone. So that's kind of cool. We're actually now able to start figuring out. So on a cold day, it's 332, but on a hot day, it was 344. So you can see that it's not a huge difference, but it does matter. It makes a difference. And so cold day, meaning this 0 degrees Celsius, that actually means when water is just about freezing. So 0 Celsius, remember, is the temperature at which water freezes. So we have all of our important puzzle pieces here, and now we are given a speed and a time, and we need to figure out a distance. Right? So how do we do that? Well, you can remember that distance is equal to a rate times time. That's kind of one way to do it. Or you can look and see that V has units of meters per second, T has units of second, and you notice that if you just multiply the two together, you get meters. So I'm going to say D is equal to V times T, and we'll use 332 multiplied by the time, which is 1 second, and hopefully you don't need a calculator to multiply by 1, because you'll just see that this is 332 meters, and the seconds cancels out. So this is my final answer here, is 332 meters. And of course there's other ways of going about thinking about this problem, but that's kind of a straightforward way to think about it. So it looks like I would guess that the answer would be C. Indeed, that is the correct answer. I encourage you to practice this one and try different scenarios. So for example, you might just try with your friend to change the numbers and both calculate this together and say, well, what if the temperature was 10 degrees Celsius? Or what if its boom came 2 seconds later? Or what if the boom came 20 seconds later? How far away would it be? Or what if I was given the temperature and the distance? And you might ask, well, how much time should I expect? Right? So all those are fair game questions, and I want you to practice those. And if you need some help, or if you want me to give you some more problems, I'd be glad to do that. All right. So we got one more question here, and then I'll make a few more comments about our homework set number 2. It's a warm and stormy night. The temperature is 30 degrees Celsius. A lightning bolt hits 700 meters away. What is the time delay before hearing the clash of thunder? So actually, this is looking at the problem from the other way around, right? So in other words, instead of being given the time and the speed, it looks like we're being given the distance and the speed. Well, you're like, well, wait a second. You didn't actually give us the speed. You gave us the temperature. And that's right. So I'm going to pause here for a moment. Now you're hopefully developing some mastery around how to handle this type of problem. And take a look, pause, and see if you can figure out what the time delay should be. Okay, we're back. So the temperature here is given as 30 Celsius. I'm going to write something down here and then I'll switch to the camera view. So 30 degrees Celsius, and the distance is equal to 700 meters, okay? I'm not going to draw the picture again because it's the same picture, so just to remind you, it's our little guy, same idea. And we're supposed to figure out the amount of time that it takes. And this is the thing we're searching for in seconds. So how do we approach this? I've got to convert this into a speed of sound. So this is going to be 344 plus 0.6 times 30 minus 20. If I notice here, 30 minus 20 is 10. 10 times 0.6 is 6. And 6 added to 344 is 350. Let me do it step by step just to help you in case you're not familiar with all these different steps here. 0.6 times 10. That was doing the result of 30 minus 20. I just left it as a 10. The next step is to multiply 10 by 0.6. So in other words, this is like sliding the decimal place over by 1. So 344 plus 6. Finally, I'm just left with a simple arithmetic here of adding 344 plus 6, which is going to be 350. And the units are meters per second. You notice that I was a little bit sloppy in that I don't carry that meters per second every step of the way. And I'm okay with that as long as you know what the units are. However, I want to strongly recommend that at the end of any problem that you solve, that you always write down the units for yourself, because you might just be surprised. For example, you might be working with centimeters per second and then assuming that it's meters per second and then realizing, oh no, it was actually centimeters per second. Oh, I should have gotten that, right? And then you have off by a factor of 100, which, okay, if you're building a bridge, this is not a very good thing, but if you're doing a problem like this, then we can always step back and try to think about what it is that you did wrong. Mistakes happen, but developing habit can actually help prevent a lot of them. So, alright, so we basically now have a speed. I'm going to go ahead and write down that we have now a speed, which is 350 meters per second. So we have the distance, we have the speed, but we need the time, how long it took. Well, I can, again, even if I can't remember a formula here, like distance equals rate times time, even if I can't remember that, I could actually look at the units here and think, well, we got meters and a meters per second. So if I did a meters and then divided by a meters per second, if you remember from our discussion about units earlier, this is like saying meters times seconds per meter. So flipping the denominator, meters cancels out and we're left with seconds. So that would be the case if I took distance divided by speed of sound. Would be equal to time. Let's just see if we can get there from also thinking about this formula here. Distance is equal to speed of sound times time. If I divided both sides by the speed of sound, here's divided by speed of sound, divided by speed of sound. Time is going to be equal to d divided by vs. Okay, yeah, it's the same thing. So, same. We're going to use this formula now. Plug in my d, plug in my v, and just see what we get. So temperature is equal to 700 meters divided by 350 meters per second. As mentioned earlier, the units are going to give us seconds. And this is 700 divided by 350 seconds. And if you notice here, oh, it's like 7, half of 7 is 3.5, so 70 divided by 35 is just 2. So it looks like we have just 2 seconds. And there's no shame in using a calculator if you need to check. But I want you to also take a look at these things and notice that often, not always, but sometimes I will give you numbers that kind of divide evenly to make the math a little bit easier. You might also notice that when you're estimating things, that you can sort of round things in such a way that gives you some even numbers to at least just see if you're ballpark correct. So based on this, I would guess that it's D. Looks like the answer is D. Good. So if you're getting all these problems, you're probably in really good shape to do the homework. There are some, lastly I'll just mention that why do all these delays matter? Why are time delays important? Well, think about a concert hall, and if you're trying to design a concert hall, you might have to think about, well, okay, where is the orchestra, right? Or where is the band? And then where are the speakers? And then the sounds are going to be bouncing off all of the walls. And the time delay is going to be actually important, as we will see, because there's effects called interference effects, and so we will need to take all of these into account. But for right now, I just want to motivate to you that these time delays really are very important, and so this is the topic that a lot of sound engineers spend a lot of time thinking about, and they consider very carefully the speed of sound, the temperature of a concert hall. All those things are important, and so if you took the difference in time, say from this cello over here to this person, and then let's say the French horn over here to this person, you might find that since the person is close enough, there's not that much time delay. But if you go over to this person who's way in the back, this big person here, you might notice that maybe there is quite a difference in the time delay. And so this could sound very strange. They could sound sort of out of sync with each other to first order. But there's some other effects which we'll get into later, which has to do with interferences. Okay. So that's most of what I wanted to say. Let me give you a couple of hints about the homework here. So we were asked in one of the problems to start making some graphs. So I showed you a few graphs, but just thought it might be helpful to see sort of a pictorial graph of this temperature thing here. So in other words, if you go back to the temperature here, you can see that the temperature in Celsius, here's temperature in degrees Celsius, and here's temperature in degrees Fahrenheit, if I wanted to plot temperature in degrees Celsius as a function of, actually here, let me do it the other way around. Temperature in degrees Fahrenheit as a function of temperatures in degrees Celsius. I'm going to do temperature in degrees Fahrenheit is T in degrees Celsius times 9/5 plus 32. So I can start plotting a couple of points on here. So for example, when the temperature in degrees Celsius is 0, the temperature in degrees Fahrenheit is 32. And the temperature in degrees Celsius is 100. 100 here, 32. Then the temperature in degrees Fahrenheit looks like somewhere over here, 212. So this here. And so you can already see just two lines. Oh, I'm sorry, I didn't switch to the camera view. Now you can see. So I just said, okay, the temperature in degrees Celsius here is 100, meaning that the temperature in Fahrenheit is 32. Is 212, and then the temperature is 0 in Celsius, which is 32 in Fahrenheit. So, good. So you can see that I've got two lines here. That's really actually enough to make a line between these two things here, and so you can actually follow that kind of line. Notice also that if I wanted to look at what the slope of this line is, well, this is the rise over run. So for example, let me just make another plot here, which is x and y. And sometimes we write y is equal to mx plus b. And here's the way that you can read this off, is that, for example, when x is equal to 0, then y is just equal to b. So that would be, this is what we call as the y-intercept. And the other cool thing we can do is that for a line, the rise over run gives us this m. So for example, if it goes up 3 for every 2 across, then the slope here is just 3/2. And so that's kind of a nice way to visualize things, is that that's the way this works. So that means that for every 5 degrees Celsius that you go 9 degrees Fahrenheit up. So hopefully that helps you to remember things, and I can certainly provide more resources about graphing if you need that. Okay, so then there's a couple other questions about calculating and using these formulae. I want you to try to use the formulae to calculate. For example, if I gave you something in degrees Fahrenheit, to be able to plug it into this formula. Of course, you can look it up on Google. You can say something like this. You can say, what is 30 degrees Celsius in Fahrenheit? And sure enough, Google's pretty smart, right? And knows how to convert these things. But I want to ask you, do you know how to convert those things? So I want you to be able to use this formulae, this one and this one, to be able to convert between the two. And that's one of the skills that I want you to make sure you're very clear on. A couple things about speed of sound. Oh, you're going to see that there is volume and surface area for a balloon. Maybe I'll just, there is a link to go to, but just in case for some reason the link was broken, the volume of a sphere is going to be equal to 4/3 pi times the radius of the sphere cubed, and the surface area of a sphere is equal to 4 pi r squared. So, anyway, you just take the radius of a sphere here, so this is a sphere, you just take its radius, if you cube it, meaning multiply by itself 3 times, and then multiply by 4 times pi, which is approximately 3.14, divided by 3, you'll get the volume of the sphere in, for example, in meters cubed. If you, for example, needed to solve for let's say you needed to solve for the radius, but you were given the area, you could use a formula like this and divide both sides by 4 pi, and then take the square root of both sides. So we'll just try that here for you. Divide by 4 pi, divide by 4 pi, and now we have a, I'll just drop this of the sphere because you know it's a sphere, a over 4 pi is r squared. And if you take the square root of both sides, remember that a square root undoes a square, and you'll be left with r is equal to the square root of a over 4 pi. So there we go. That's how you would do something like that. Maybe that's going to be very, very similar to something that you see on the homework. Lastly, one of the homeworks, you're going to be going to a simulation, a sound simulation. This is something similar to what you did, but you can, for example, type in PhET sound simulation, and it's going to be that first link here. And when you run it, you're going to have Java installed. If Java is not installed on your computer, you should install Java. You also may need to open up this app from your, if you're using a Mac, you'll have to open it up by going to where the file is and then opening it there. And I won't open it right now, so that's the idea. And also I want to mention that all of our computers in the library have Java installed and are able to run this program. So if you're running into trouble, block yourself off, half an hour or so to go and spend time with this simulation. It will certainly help you make sense of the things in this class. So alright, I think that is it for now, and I will continue on next time. It looks like we'll be talking about period and frequency. So I think you have now everything you need for homework 2. Oh, yeah, actually, you know what? Actually, here, I'm going to maybe just start in on a little bit of the material for, this is also chapter 1 type stuff, but I wanted to say, how does mass affect frequency? And so we're going to go into this in more detail next video lecture, but I want to just give you what you need here is that if you put more mass on a spring, let me see if I can even do this. So here's a little animation. If you have more mass on the spring, then the time that it takes to go up and down becomes longer. In other words, the frequency becomes less, and there's actually, or you can say that the period becomes more as you can make it heavier. And so I'm going to skip ahead here. So there is a formula, and you'll see this here in your book here, that the period, in other words, the time that it takes for this spring to go up and down, is going to be on page 5 of your text. And so if I kind of go over here, you'll see this is the formula here, frequency, and it looks like a really complicated formula, but really all it's saying is that if you made a spring stiffer, meaning that it's more like a shock absorption spring on a car rather than a slinky, then it would oscillate naturally at a higher frequency. If you also put more mass on the spring, the more mass you put on there, the lower the frequency. So that hopefully will help you to solve these things. I will say that the way that you can think about these things here is that if frequency goes like 1 over the square root of the mass, and just write it as m right now, then imagine that you have some frequency 1, and we're not even going to worry about the stiffness right now or the 1 over the 2 pi. Just imagine you have this formula here. And imagine that I took the mass and I instead turned it into 4 times the amount of mass. Well, Now what's the new frequency? Well, the new frequency here is going to be 1 over the square root of 4m, which is going to be 1 over the square root of 4 times the square root of m. So if you notice, that's 1 over 2 times 1 over the square root of m. That here is F1. So in other words, making the mass become multiplied by 4 is actually going to make the frequency divided by 2. So hopefully you can see that connection there. I want you to start to think about this idea of scaling. And so like, for example, if the mass increases by a factor of 2, then we would have a square root of 2 down there. So that would mean that the frequency would divide by square root of 2. So, and so on. And so the square root of 2 is approximately 1.4. You can put that in a calculator, you'll see that. So anyway, I think that's all you need for your homework. Yeah, and maybe I'll just also mention that this is an idea about complex periodic motion. You can actually see that all of these things are periodic in the sense that they are repeating themselves over and over again, but it doesn't have to be like a perfect sinusoidal wave in order for it to be. This is like a perfect sinusoidal wave here, and this is sort of still something that's periodic, but it's not happening in this exact, how do you say, sinusoidal way. So we'll talk more about this next time, but I just wanted to give you everything that you need to be able to confidently march forward and be able to complete homework number 2. All right, thank you.